Hi everyone! In this video we're going to continue our discussion on cardio, or determining the relative strengths of acids. So in the last video we went over charge, atom, and resonance. So we saw that if a conjugate base has a charge, it's less stable, so then the acid is less or is weaker. And then we saw that if your conjugate bases have the same charge, you can compare them based on their atom. And whichever atom is more electronegative or larger in size will be more stable. And then we saw that if you can't figure it out based on charge or atom, you can determine the strength of an acid based on if its conjugate base has resonance. So if a conjugate base of an acid does have resonance, that means it's more stable, so the acid is stronger. Now, let's say that you've already ruled out charge, atom, and resonance. The next thing you'll check for is dipole induction. All right. So let's compare two acids again. So we're going to compare acetic acid, which we saw last time, and we're going to compare that to trifluoroacetic acid. So this is going to look very similar, except the carbon on the left-hand side will have 3 fluorines bonded to it instead of 3 hydrogens. All right, so again, we've got acetic acid up above, and then trifluoroacetic acid down below. Okay, so let's try to figure out which one is stronger. And again, we're comparing the conjugate bases and their stability. All right, so let's draw out the different reactions. And if you want to try to determine the products on your own first, feel free. You can pause the video. All right, so let's see what the products are here. So we already know what the products are for acetic acid, right? We did this last time. We saw that the base is going to grab onto the hydrogen on our carboxylic acid, and then the lone or the shared pair of electrons there is going to end up on oxygen. So we get a negatively charged oxygen, and I'm going to write the conjugate acid down below because remember, this product has a resonance structure. We saw this last time. So let's draw that out. Oh, and I forgot my lone pairs on my oxygens. Oh my goodness. Okay, so now we have our resonance structures here. And I'll draw brackets around them. So now what about our trifluoroacetic acid products? So a similar thing will happen. The base will grab onto that hydrogen, and then the shared electrons between oxygen and hydrogen will end up on oxygen. Okay, so we will end up with a similar product, except again, we'll have 3 fluorines on that carbon on the left. And again, I'm going to write the conjugate acid down below because you can probably already see that we have resonance in this product as well. It looks very similar to our previous conjugate base. So we can show that there is resonance. Okay. So again, we've ruled out charge. Both conjugate bases have the same charge. We've ruled out atom. They have the same atoms for the most part other than those fluorines, right? But we're really focused on the oxygen because the charge is on oxygen. We've already ruled out resonance because both products have resonance. So now we're on dipole induction. So what does dipole induction even mean? Well, we're trying to figure out if there's a dipole moment for these two products. So there is technically a dipole moment kind of going up towards those oxygens, right? But we really want to compare the two conjugate bases and see if one of them has a greater pull of electrons in a particular direction, and if that's going to stabilize the molecule. So again, the one difference here between the two products are those fluorine atoms. Now remember, fluorine is very electronegative. So what that tells me is that there is a dipole moment or dipole induction towards those fluorine atoms because fluorine's going to pull electrons towards itself, even more so than oxygen, right? And I'm going to draw the same thing for our resonance structure too. Now, looking up above at the conjugate base for acetic acid, it does not have that same pull of electrons because it doesn't have an electronegative atom like fluorine. So would that dipole moment in the molecule down below stabilize that molecule? So is the conjugate base of trifluoroacetic acid more stable or less stable? So it is actually more stable, and that is due to that dipole induction or that pull of electrons. And remember, when we talked about resonance structures, we said that if an atom can share its negative charge with another atom, that will stabilize the molecule. And it's the same thing with dipole induction. So those fluorine atoms are kind of pulling electron density towards them and away from oxygen. So that negative charge is getting kind of pulled away from oxygen a little bit, right? And that's going to stabilize the molecule overall. So this is more stable due to dipole induction. So really, if a molecule has any opportunity to spread out its charge, it will, because that will stabilize it. Okay, so trifluoroacetic acid has the more stable conjugate base, so it is the stronger acid. All right, and if you want more practice with dipole induction, I recommend the Skill Builder exercise 3.7 on page 110, and that is specifically focused on dipole induction. All right, so what if we've ruled out everything so far? What if we ruled out charge, atom, resonance, and dipole induction? The next thing we'll focus on is orbitals. Now remember, this is the least important out of all of the different factors we've talked about, but it can come up sometimes. Very rarely, but it does come up. So let's compare two acids. We're going to compare methane, and I'm going to actually draw the Lewis structure this time because I kind of want to think about orbitals here. So I want to think about steric numbers and hybridization. And we're going to compare methane to a molecule called acetylene. And acetylene has 2 carbons with a triple bond, and each carbon has a hydrogen. Okay, so again, we're asking which acid is stronger. And again, we're comparing the conjugate bases and their stability. All right, so let's figure out what our products would be if each of these molecules reacts with a base. And if you want to try this on your own first, feel free. You can pause the video. Alrighty. So let's look at the products of this, or of each of these reactants. So in the first reaction, we've already seen previously, this base is going to grab a hydrogen, and then the shared electrons will be left on carbon. All right, so our products are CH3, and the carbon has a lone pair, so it has a negative charge. And you can calculate the formal charge if you want to double check and make sure that's true. And then our other product is our conjugate acid. All right, so let's do the same thing for acetylene. The base is going to grab a hydrogen, and then the shared electrons will be left on carbon. And we could have taken either of those hydrogens. The molecule is symmetrical, so either one is fine. We get the same product. All right, and our other product, the conjugate acid. Okay, so now let's compare our 2 conjugate bases. And I'm just going to highlight them again. Okay, so they both have the same charge. The charge is on the same type of atom, carbon. There's no resonance here for either of these conjugate bases, so we're ruling that out. And there's really no dipole induction for either of these products either. So all we're left with is orbitals. So let's figure out the hybridization of each of these negatively charged carbons. So for the first product, what is the hybridization of that carbon? So if you're not sure, let's think about the number of bonded atoms and lone pairs. So we're trying to figure out the steric number. So it has 3 bonded hydrogens and 1 lone pair. So its steric number is 4. So what is its hybridization? sp3. Okay. And then what about the carbon in our other product down below? What is the hybridization of that carbon? So let's start with steric number. What is the steric number of that carbon? 2. It's bonded to another carbon and it has a lone pair. So there's 2 groups there. And if its steric number is 2, what is its hybridization? sp. Okay. So how does hybridization play into stability? Well, let's think about the shapes of these hybrid orbitals. So remember, sp3 hybrid orbitals have more p character. So those orbitals are longer, right? And then sp orbitals have less p character. So sp3 has 75% p character. sp only has 50% p character. So sp orbitals are shorter. All right. So now let's think about if we have an electron in an sp3 orbital. So let's kind of draw an sp3 orbital versus an sp orbital. And we have an electron kind of floating around. Would an electron in an sp3 orbital be closer to the nucleus compared to an electron in an sp orbital? Or would it be further away? So if you have an electron in an sp3 orbital, that electron can be farther away from the nucleus. But if we look at an sp orbital, that electron is going to be much closer to the nucleus on average. So electrons are closer to the nucleus in an sp orbital. And do electrons like protons? Yes. So that means electrons like to be close to the nucleus where the protons are. So that's actually going to stabilize the electrons and therefore the molecule. Okay, so again, that negative charge on the sp carbon is closer to the nucleus and closer to the protons in the nucleus. So that stabilizes that conjugate base. So acetylene is actually the stronger acid. So that's kind of a weird concept, right? We're digging so far deep into these molecules and really thinking about their hybridization, the length of the orbital lobes, where electrons are around a nucleus based on those hybrid orbitals. So again, orbitals doesn't really come up that often when we're trying to figure out relative acidity. And if we look up the acidity of methane and acetylene, they're really not that acidic. They're pretty weak. So again, this is the least important factor in cardio. But if you want more examples, I recommend trying Skill Builder 3.8 on page 112. Okay, so we've gone over the full cardio characteristics. So we talked about charge, atom, resonance, dipole induction, and orbitals. So I think I'll stop there, and in the next video we'll go over some practice problems, and we'll try to decide which acid is stronger based on all of those different factors. And I'm going to make it a little more challenging. So I'll see you then.